Okay, this talk is going to deviate a bit from the other, from the previous ones, as it is more focused on things we can do with light fields and in recreating visual cues. So it is not that much about studying the subjective experience and quality of experience in immersive media. However, it somehow contributes to the topic. So I will briefly introduce the light field as we formalize it, then light field displays and how they recreate 3D visual cues. I will focus more on the epipolar plane image representation and format of densely sampled light fields, which we like to put forward, and how we can reconstruct it from a sparse set of cameras. So we usually start with this planoptic function, which is the 7D function representing all rays traveling in space, parameterized by their location, direction, wavelength, and time. And we usually drop the wavelength and time because we can work with trichromatic representation of color, and then we can play with sequences. And if we consider this propagation in half space, we end up with parameterizing the rays through their coordinates when they are passing through two parallel planes, which are usually associated with camera plane and image plane in an image-based representation. So such a parameterization gives us a way to think of rays either in their Cartesian coordinates or in their polar coordinates, where for small angles we can directly replace the angle with its tangent. So depending on the application, either Cartesian or polar coordinates might be preferred. And we can also consider how rays propagate in space. When put then as samples in this ray space coordinate system, such propagation is usually related with the shearing operation, which will play a role later when we speak about the epipolar plane representation. So what we usually do when we deal with light field displays is to study first how human eyes sample the light field, and we can represent the position of the eyes over the array space, and then consider how they move, and this will give us a kind of ray space sampling related with the human visual system. And then from the other side, we can try to model the light field displays as recreating the same light field on the same coordinate system, or matching what the human visual system can see. And essentially why we are interested that much in light field is because light field can be the tool for recreate more visual cues. What we know from earlier attempt that stereoscopic 3D or binocular 3D recreates only the stereopsis, the binocular visual cue. It usually fails to recreate the focus cue and the continuous parallax. So focus cue is related actually with two phenomena. One is the accommodation. One, the crystalline lens are forced by muscles to change the shape in such a way that the point in certain depth gets in focus on the eye. However, there is also the other effect called retinal blur, when points which are at different depths appear like blurred on the retinal image. So usually these two effects work in accord in the human visual system, and this is how we perceived elements, objects in focus. And then if we start moving the eyes, like the retinal image will change, and then we'll have the effect of motion parallax. actually, may I return here? So what we require from light field displays is to ensure this ray directionality, which will support the focus cues and the motion parallax. So we need tools, we need technologies which will exactly ensure both spatial and angular sampling and reconstruction. And there are different display technologies aiming at doing this. We can look at integral imaging, and actually the common part is that you need to have generators. In terms, it can be some 2D display, it can be TFT or LCD or some other matrix, and then you need to have modules which ensures the directionality. So it can be, for example, a sheet of lenslets, and these are the cases of integral imaging or super multi-view displays. Or you can have also differently positioned projectors at certain distance from the screen, recreating this directionality. Basically, differences are how you ensure this directionality. For example, in the super multi-view display, the focal plane of the micro lenses is positioned as the viewing plane, and then the pixel behind the micro lens contribute to different view images. So one has to take care of how pixels corresponding or rays corresponding to different directions are combined together. And usually what we need in such displays is that we need a high number of views. So in contrast to what actually Federico was presented, we are looking at light field as something which can support more visual cues. So we are not interested in showing flat 2D images, but interested more in how we can develop computational tools for faithful reconstruction of these rays from the real world imagery, and then to support these displays which are still emerging. So these displays are still under development, but hopefully they will come in one or another form. So in a pursuit of way how to form or reconstruct a light field from real scenes, we come to this epipolar plane image representation, which is another way to look at parametrization and the rays in terms of two parallel planes. So the example is that we are having camera moving like from position A to B, C, D, and so on. So this will be different perspectives of the scenery. And if we order these images along the t-axis, we'll get a kind of three-dimensional structure. If we start moving the cameras also vertically, we'll get the four-dimensional structure. And then we can look at different combination of coordinate axes. Like when we look at the multi-perspective images, we see 2D images. However, if we combine the camera axis and one of the image axes in a slice like this, we are going to see this directional structure where different points at different depths transform into lines with a certain direction, and the direction is related with the depth where the points are. So you can see we can determine actually the direction by knowing the two camera positions and the corresponding projections at the images. So in a sense, epipolar plane image encodes the geometry of the scene into the shapes of these directional stripes formed by epipolar lines. Everything is very good until we, okay, this is something explaining in more details. Like if we make the slice here, like you can think of going into t direction, we are going to see a homogeneous image, so it is somewhere in the background. Then if we make the slice here, we are going to get the same points, their evolution along the direction of the camera motion. And when we make these different slices, we can see different structures of the scene encoded in different epipolar planes. We can do the same in vertical parallax as well. So in this way, we are going to have a 4D epipolar image cube, and we can get the combination of either of slices. What I wanted to say is that everything looks okay as soon as we consider this in continuous time. So this means infinite number of dense cameras, like any position of the camera. And if we take such an epipolar image and transform it into Fourier domain, the directions will transform into a specific support of the Fourier transform, which we can call bow tie or a fan, which is limited by the minimum and maximum depth of the scene and the focal length of the camera system. This is strictly for Lambertian scene with no occlusions. So then if we start getting occlusions, we'll see that this Fourier transform and its support changes. Now, when we start discretizing the Fourier transform, which means placing discrete number of cameras, and each camera has a discrete number of pixels, we are periodizing the spectrum. So in spatial domain, it will look like this, and in the angular domain, it will like this. So we get all possible replicas, and our light field reconstruction task is to be able to preserve the baseline and to get rid of these replicas. This is good when we have dense cameras and dense pixels in each image, because then the replicas will be further away from each other. However, we may experience also the case when the cameras are sparse, and then the replicas will overlap, and we'll end up with aliased representation of the light field. So the discretization in spatial and angular domain impose these challenges. So if we want to recreate smaller features, we need more pixels. If we want to recreate closer objects, we need denser set of cameras. And then optimal sampling and related with reconstructions depends on our application and what we want to reconstruct. There is this figure, which is quite well known from the seminal paper on planoptic sampling. Then we either work with more images or with more depth layers. And there is always compromise how we sample. Do we sample a higher set of images, or we go at sampling higher or dense number of depth layers? When we encounter occlusions, the support of the Fourier transform of the light field gets wider, and we need better tools for its reconstruction. And here is actually the time when I want to comment on the what we called densely sampled light field. When we start moving the cameras to position the cameras at different perspectives, this is like the sampling interval, sampling distance between cameras. This multi-perspective representation appears in form of pixels being projected at different pixel positions. what we'll see as a disparity between images. So if we put the cameras further away, like the disparity, like this is like disparity of 3 pixels. So the point project on pixels where the disparity vector is 3 pixels. If we go close enough, like less than 1 pixel or 1 pixel at most, then there is no ambiguity in putting the line, in putting the epipolar line. Here, we don't know exactly where to go here or here. And with disparity less than 1 pixel, the lines are formed unambiguously. So this is actually what we want to achieve. We want to be able to form the epipolar lines in an ambiguous way. Otherwise, we'll have to deal with some other tools if we want to recreate the continuous planoptic function. Here we can deal with simple linear interpolation if we need to create arrays different than the array on the densely sampled grid. So our task is to recreate all images which are in between the given ones. So if we start with a set of captured views, which is sparse, let's say coarsely sampled light field looking in epipolar image domain, we want to get densely sampled out of this one. In terms of Fourier transform, this means that the replicas will be nicely separated, while here the Fourier replicas are overlapped. So we are dealing with this aliasing. If we get the views and put them together, like dealing, for example, with views which are 16 pixels disparity away, if we put them together, we will see this kind of staircase pattern. If we put them at the proper places with respect to the densely sampled light field, we can see that the lines start to form. But we can see because we are human, so we know how to get the entire from patches. But how to tell the algorithm or the computer to continue the lines. So it seems that this is a problem which can be cast as an in-painting problem, like in imaging. When we have holes, we want to in-paint the holes. And one modern tool for solving in-painting problems is to go through sparse image representation. So what we want to achieve is the following. So we want to find, let's say, Y is our image. We want to find it in some representation in terms of some dictionary. So these are, alpha is representation of the image with respect to this dictionary. And we want to find it in such a way that when subsampled, the difference between the representation and the given image is minimized. And we minimize it along with looking for such a representation which is sparse. And this will ensure that as soon as we can find a representation which reconstruct the given samples, we are good. Also given that the sparsity is ensured. So our dictionary is formed by what we call shearlets. Those are compactly supported time frequency atoms. So in space domain, they look like oscillating filters. And in Fourier domain, they look like differently oriented multi-scale filters. So we have one atom responsible for the low frequency region, and then we get different scales, and in each scale we'll have several directions. So we can go further, we can increase the Fourier, the support, and we can support more directions and at higher scales. So having such a dictionary, we can slightly change the notations because they follow in the next slide. So we say this is our shearlet transform. So we have a direct transform which takes the image and decompose it into a set of coefficients. And then we have an inverse transform which takes the coefficients and reconstruct the image. So these transforms, they exist in terms of sampling theory. They form a frame, so the reconstruction is ensured, and so on. So we can kind of, this is an equivalent formulation of our problem. So find the sparsest representation in shearlet domain, which ensures that our image can give the same given views. So H here is this masking operator which takes sparse sampling from this densely sampling. Such problem is solved, like the sparsification is done usually through thresholding. So what we are going to do is to take our image into shearlet domain and keep only the significant coefficients and zero the other ones. And this is usually done through iteration. So at each iteration, we subsample the image. We take the difference with the given views. There is one factor responsible for the convergence. Then we add it to the given iteration. We take it into shearlet domain where we threshold it, and then we reconstruct it back, and this is our next iteration. This turns to be quite powerful in filling the holes. So if we start with something which is very low frequency, so you see after each iteration we are getting more and more details. So like the blue or the turquoise rows are the given views, and all others are views to be filled by the procedure. And in terms of views, this means that we can start with 16 views, and then I'll try to run it once more, but it seems that no, it doesn't start. So the idea is that we show the input views, and we show the reconstructed against the ground truth, which seems to be quite the same. Recently, we managed to reconstruct even non-Lambertian scenes, which is usually impossible with interpolation dealing with depths, because in the case of non-Lambertian scenes, the depth might not be unambiguously defined. So for example, reflective surfaces, the shearlet atoms are quite capable of reconstructing the intensity. So you can see here it rotates. And here is a zoomed in version where you can see that these areas are quite nicely reconstructed compared with one of the state-of-the-art methods. This is a difference image showing that much more details are reconstructed than in the state-of-the-art approach. So just to conclude, we are looking at light field technologies as candidates for recreating 3D visual cues. So we believe that immersive visual experience is possible if all visual cues are recreated in a synchronous way. So we need to have stereopsis, we need to have focus, we need to have continuous parallax. And the tool of doing this is to be able to generate dense enough set of views, correct views. And we specifically have developed such a computational imaging tool for reconstructing densely sampled light field. And given a particular display, then we can pick up the rays which are needed for the display. The procedure is still slow. In parallel implementation, it takes seconds, so it is still to be further developed to run in at least in interactive times or real times. And then, of course, there are other challenges related with what exactly light field display technology can be developed. Whether we need lenslets, whether we need projectors, or some holographic elements, or something which will support the desired directionality of rays. Okay, this was the last slide. Thank you for your attention. Yes, please, questions.
Do you have any idea how many number of samples you require to basically reconstruct using the shear lifts, the continuous representation?
Theoretically, we can start with quite subsampled set of images. So experiments like the images are separated by, let's say, disparity of 64 samples. Yeah. It will require more layers of the shear-led decomposition because you have more candidate directions. And then you need to introduce more layers. So let's say when your input images are close to each other, then you need to have atoms which are dealing with the corresponding directions in things like this. If you start having these holes wider, then you have to test all these directions, which means more scales and more directions, which increases the size of the dictionary, the number of your atoms. Also, you need to have more views. Like in the procedure, in the thresholding procedure, we keep the given samples. Like here, like they work like pillars. So you always enforce the existing things in order to steer the directions which each of next iterations. So as you see in the demonstrations, the details are being restored, like from stronger to weaker to more details.
The second question I had was, you told me that you also did some experiments on non-Lagrangians. You said reflections, basically.
Yes.
Have you tested anything on transparencies?
Semi-transparent, yes. So we have already, I didn't show this example. Semi-transparency is like you have an object and in front of it you have another object which is semi-transparent. Again, if you try to find the depth in such a scenery, this is very challenging. You cannot have an ambiguous depth associated. Yeah.
Let's say car glass or something, and it's reflected.
Yes. Yeah.
Something is being reflected.
We have such a demonstration in the lab. Sometime we can show it also on the big light field display. This type of decompositions are dealing quite nicely with it, because they are kind of combination, signal expansion in terms of coefficients. So it is like the intensity which is seen in the multi-perspective images, and they are able to handle such cases. What was more surprising for us, because initially we were thinking that such problems with reflections won't be easy to handle, because in the reflection you actually change the directionality in a kind of orthogonal direction. So you need atoms which would support this direction. However, what was actually discovered, that we can scale the scene and shear it in such a way to confine it within the support of the dictionary we have. So it is a matter of a technical tweak to put the scenery in such a way that in terms of a shearing operation, it will be inside the reconstruction atoms. And then they are able to handle it. Then you have to de-shear it to reconstruct it in the proper views and proper images. Of course, the challenge is to find out how much you need to do this, to shear it properly, which depends on different factors. And
so,
yeah.
I'm just imagining if you have a scene where you have non-Lambert objects that are moving around. So this is still static. We haven't experimented with non-Lambertian moving objects. This is kind of very interesting and has to be tried. Yes, please.
So, yes, the Charlotte dictionary looks very, it's pretty smart because it's kind of systematic dictionary, and seems pretty nice fitted with this EPI presentation. But you partially answer one of my questions, that was how you deal with this reflection stuff. But do you think there is a room for learning new dictionaries, so not less systematic learning a dictionary?
Yes, there are. Currently, there are plenty of works taking this path. Yeah. So you can train your dictionary, and you can train it on light field patches. So there are such works where the patches can be either 4D patches, which are kind of following also the, when they are considered in epipolar image domain, they are patches which will reveal the directionality. And then you need to have a good training set to build the dictionary. So then the task will be to find simultaneously the dictionary and the coefficients. So you have to learn the dictionary. This is the task of sparse coding. Yes.
So I introduced one of our methods that was using convolutional sparse coding.
This is, we have followed several works which are focused on sparse coding and learn dictionaries. One of our aim is to compare with them. They perform extremely well if you have a very good training set. If you have a feature which is not in a training set, you won't catch it in the normal. So what you mentioned, this systematic way, is exactly the alternative path. So we are dealing similarly what was done in imaging with curvelets, contour nets, all other directional nets, which aim at ensuring certain rate of approximation when you are taking n coefficients of the representation. Here, the good work which was done is to recognize that such directional elements and multi-scale elements are very good to tile the frequency space. But of course, we also have, like, there are different problems in this. So we have to work, for example, we call it sparse, but it is not, in practice, you need to use all coefficients. So you get like 30, 60 coefficients per sample when you are doing the reconstruction. All right. If there are no other questions, this was the last talk of this quick workshop we organized. Thank you very much for your attendance, and we hope to have more of this in the future because the area is quite interesting. Thank you very much.